Okay, now for HCl, it reacts with water to form hydrogen ion plus chloride ion, or else we can write H3O positive plus Cl minus. So hydrochloric acid reacted with water to give the hydronium ion plus the chloride ion. So here, hydrochloric acid acted as an acid and water acted as a base. Why? Because as you see in this equation, hydrochloric acid donated a proton to water and water accepted it, forming the hydronium ion and the chloride ion. So hydrochloric acid is acting as an acid and water is acting as a base. When hydrochloric acid acts as an acid, it forms what we call a conjugate base of hydrochloric acid, which is the Cl. What is left from the hydrochloric acid is the chloride ion. So we say that the chloride ion is the conjugate base of hydrochloric acid. And since water acted as a base, then the hydronium ion will be the conjugate acid of water, because water here is acting as a base. So the hydronium ion is the conjugate acid of water. Now, if we take another example, ammonia plus water giving ammonium ion plus OH ion. So here we say that here, when we look at this equation, we'll see that here water donated the proton to ammonia. That's why it gave ammonium ion, and what is left is the OH ion. So here, since water donated a proton to ammonia, water is acting as an acid, and ammonia that accepted the proton is acting as a base, forming the conjugate ammonium ion will be the conjugate acid of ammonia, and the OH ion, which is left from water, will be acting as a conjugate base for water. So we say that here HCl and chloride ion are acid-base conjugate pairs, acid-base conjugate pairs. And also we say that water and hydronium ion are acid-base conjugate base pairs. And here the same, ammonia with its ammonium ion are acid-base conjugate pairs, and water with the OH ion are also acid-base conjugate pairs. As I told you here, we always say acid 1 base 2 gives acid 2 base 1. It's always written in this way. Acid 1 reacting with base 2 gives acid 2 plus base 1. So the conjugate acid-base pairs take the same number. Okay. Now, as we look here, we will see that water is acting here as a base, and here it is acting as an acid. So what do we call water? Do you remember the name? What do we call water? When something acts as an acid and can act as a base, what do we call it? Do you remember or not?
No,
yes. We call water here, we call it an amphoteric compound. We call it amphoteric. When a substance can act as an acid and can act as a base, we call it an amphoteric substance. Like when we said, for example, the other example we took yesterday, last time, is that sulfuric acid, when it reacts with nitric acid, although nitric acid is a strong acid, yet here it will react as a base because it can accept a proton from the sulfuric acid forming hydrogen sulfate, and the nitric acid forms H2NO3 positive. So here, although nitric acid is one of the strong acids, yet in this equation is acting as a base when it is present with sulfuric acid. Sulfuric acid is stronger than nitric acid. So the sulfuric acid acted as an acid and donated a proton to nitric acid forming H2NO3 positive, and sulfuric acid itself became HSO4 minus. So here nitric acid is also an amphoteric substance. It's acting sometimes as an acid, and at other times it's acting as a base. Now, Acids and bases are divided as strong acids and weak acids. Also, bases are divided into strong and weak bases. Now, what is the definition of a strong acid? What is the definition of a strong acid? Do you remember?
Yeah, it breaks down completely and gives
Yes,
off many ions.
yes, excellent. So always, if we have a strong acid, it completely ionizes in water, forming hydrogen ions and chloride ions. For example, any strong acid completely ionizes or completely dissociates into its ions, which means that if we started with a certain concentration of hydrochloric acid, then we will get the same concentration of both ions. And this means that the concentration of the hydrogen ions will be equal to the concentration of the acid. And in case of weak acids partially dissociates or partially ionizes in water. Like, for example, if we take something like ethanoic acid, we say it partially ionizes, and we draw an equilibrium arrow to show that it partially ionizes into hydrogen ions and ethanoate ion. And so this means that if we started with 0.1 mole per decimeter cube of ethanoic acid, we cannot say that the concentration of hydrogen will be the same, because only 10% maximum of ethanoic acid had dissociated into hydrogen ions and ethanoate ions. Only maximum between 1 and 10% only dissociates, and the rest will be in the form of ethanoic acid. So here we have an equilibrium, because 90% is present in the form of ethanoic acid and only 10% dissociated. So we have equilibrium. And as we know that whenever we have equilibrium, we can have what we call an equilibrium constant. We know that all equilibrium reactions have what we call an equilibrium constant, and here it is going to be called the acid dissociation constant. It's going to be called acid dissociation constant. So whenever we have equilibrium, we have an acid dissociation constant because this is an acid. So always weak acids will have this acid dissociation constant. If we want to differentiate between a strong acid and a weak acid, for the weak acid, they are always going to mention that it has a certain acid dissociation constant. But for the strong acid, they will not mention anything about Ka value. So we will know that it's strong acids. And also, as I told you last time, that we have HCl, we have sulfuric acid, we have nitric acid. These are strong acids. But if we have ethanoic acid, or if we have, for example, hydrogen fluoride, hydrofluoric acid, these are weak acids. Okay. Now, we said that since the concentrations of the acids and bases are so small, then we are going to use a term which is called the pH. And what is the pH? It's a logarithmic term. We are going to do it for the hydrogen ion concentration in order to get whole numbers. So the P means minus log. So pH means minus log the hydrogen ion concentration. So in acids and bases, we must calculate the pH in order to find out whether our solution is acidic, basic, or neutral. So because we know that for the pH values from 0 to 7, we have acidic solutions. From 7 to 14, we have basic solutions, and neutral solution at pH 7. So whenever we calculate the pH and find it lies below 7, this means that we have an acidic solution. If we calculate it and find it to be above 7, then it's a basic solution. Now, how do we calculate pH values? We said that it depends whether we have a strong acid or a weak acid. This is for acids. And of course, we are going to see how to calculate the pH for bases. Now, for a strong acid, And since we said that a strong acid completely ionizes to give its hydrogen ions and other ions, then if we start with a concentration of 0.1 mole per decimeter cube, this means that the concentration of the hydrogen ions and chloride ions are the same. But we don't have to do anything with the chloride ions. We are only going to deal with the hydrogen ions. So we say that the pH equal minus log the hydrogen ion concentration, which means that we say minus log 0.1, and this is going to be, I think it's going to be 1, but I'm not sure. Let me do it. And you have to minus log 0.1. Yes, this is equal to 1. Minus log 0.1 is equal to 1. Okay, so for any strong acid, we just take the concentration of the acid itself, because the concentration of the acid itself is the same as the concentration of the hydrogen ion. They are equal. So we take minus log the concentration of the hydrogen ion, it's the same as minus log the concentration of the acid itself, and we get the pH value. Okay, understand this, or shall I repeat it?
First understood.
Okay, so whenever they give you any acid with any concentration, just substitute for the concentration of the strong acid here instead of the hydrogen ion concentration, and you get the pH. Now, what happens if we have a weak acid? When we have a weak acid like ethanoic acid, for example, it partially dissociates into hydrogen ion and ethanoate ion. And we said that whenever we have equilibrium, then we have an equilibrium constant, which we call it here acid dissociation constant. And we say that the Ka equal the product of the products, means the hydrogen ion concentration times the ethanoate ion concentration, divided by the concentration of the acid. Now here we have, in this equation, we will see that the concentrations of both the hydrogen ions and the ethanoate ions are equal. They are present in the same mole ratio. So we can substitute for the ethanoate ion by hydrogen ion because both are equal. So we can remove this and put H positive instead. And this means that we have hydrogen ion concentration times hydrogen ion concentration divided by ethanoic acid concentration, which is equal to hydrogen ion squared divided by the concentration of ethanoic acid. Or we can say that the hydrogen ion concentration, which we want to find out, is equal to the square root of Ka, which is the acid dissociation constant, times the concentration of ethanoic acid. Of course, here we did an assumption. We did an assumption to say that as if the concentration of ethanoic acid, ethanoic acid did not dissociate at all. When we take here the concentration of ethanoic acid, the same as they give us here, for example, if they give us here 0.1 mole per decimeter cube, and maybe they give us a value for Ka equal 1.74 times 10 to the power minus 5 mole per decimeter cube, maybe they give us these values, then here we are going to substitute by these values in the equation. The Ka 1.74 times 10 to the power minus 5, and we substitute for the concentration of ethanoic acid to be 0.1. Although part of the ethanoic acid dissociated, we make an approximation as if it did not dissociate. We substitute here by the value of the ethanoic acid that we started with. So this is an assumption, this is an approximation. As an approximation, we will say that as if the ethanoic acid did not dissociate, so we are going to take its value and substitute by it at once in our law. If you do not remember the law, then you have to do these equations in just 2 minutes, and you will find out how to get the hydrogen ion concentration. We did find it out by writing the equilibrium constant, Ka, equal the concentration of the products times each other divided by the concentration of the reactants. And since both products have the same concentration, we can remove the concentration of ethanoate ion and replace it by H positive. And in this way, we will have H plus squared divided by the ethanoic acid concentration. And this means that if we do cross multiplication, then the hydrogen ion concentration equals the square root of Ka times the ethanoic acid concentration. Now we got H positive, so this means that the pH equal minus log the hydrogen ion concentration. And of course, we are going to substitute by the value that we got here. Okay, Salman, or shall I repeat it?
Yes, sir.
Okay, now what happens if we have a base and not an acid? Then we have to know about something called the ionic product of water. The ion product of water. What is the ion product of water? Now we say that water very, very slightly dissociates into hydrogen ions and OH ions. The water dissociates very, very slightly to form hydrogen ions and OH ions. And since we have here partial dissociation, then this means that we have an equilibrium constant, like what we always do. Now, the equilibrium constant K equal the concentration of the hydrogen ion times the concentration of the OH ions, as we usually do. The equilibrium constant equal the concentration of the products times each other divided by the concentration of water, which is our reactants. Or else we will remove or we transfer the concentration of water to the other side. So we say that K times the concentration of water equal the concentration of hydrogen ions times the concentration of the hydroxide ion. Now, K is a constant. We call it equilibrium constant. So it's a constant. And since water very, very slightly dissociates, this means that we are going to consider the concentration of water to be also constant because it did not change. We are going to assume that it did not change. Why? Because its dissociation is so small, as if the concentration of water is constant, did not change. So if we multiply K, which is the equilibrium constant, by the concentration of water, which is considered as constant, then we get a new constant that we are going to call it Kw, and we call it the ion product of water. The ion product of water, which is equal to the concentration of hydrogen ion times the concentration of the hydroxide ion. Okay. Now,
So, Miss, what we're calculating here is estimates, right?
excuse me?
So what we're calculating here is estimates.
Yes, it's an approximated value, ولكن we do it. يعني it's done. يعني it's going to be considered in all our problems. We are going to solve by this law. Okay. We assume, you mean that we assume that the concentration of water is constant, isn't it?
Yes.
Yes, we assume that it is constant, but it's very nearly constant. Why? Because we said that the dissociation of water is very, very
slightly.
small. Yes. So we are going to consider as if it did not change. Now, scientists found out that Kw at 298 Kelvin, which is 25 degrees Celsius, the room temperature, they found that Kw has a value of 1 times 10 to the power minus 14. They found this value for Kw at room temperature, 298 Kelvin. And this means that if we take 1 times 10 to the power minus 14 equal the concentration of hydrogen ions times the concentration of OH ions, and since both ions have equal concentrations because they are produced in the same mole ratio 1 to 1, so this means that these two concentrations of hydrogen ion and OH ions are equal, and this will let us find out that the concentration of hydrogen ion, which is also equal to the concentration of the OH ion, so each of them will be equal to 1 times 10 to the power minus 7. That's why when we take pH of water, which is minus log the hydrogen ion concentration, which is minus log this value, we get a pH of 7. That's why we always say that the pH of water is 7 at room temperature. And we got this 7 from these calculations, that the Kw, the ion product of water, is equal to the concentration of the hydrogen ions times the concentration of the OH ions, and the Kw is 1 times 10 to the power minus 14. And since these two concentrations are equal, so every one of them has a concentration of, we take the square root of this Kw, we get 1 times 10 to the power minus 7, which means that the pH of water is 7. Okay, understand till now?
Yes, ma'am.
Okay, so here, if they give us in a problem, they give us that, for example, a solution has, for example, a 0.1 mole per decimeter cube of sodium hydroxide solution. They give us that we have a 0.1 mole per decimeter cube sodium hydroxide solution. They say, find out its pH. Find out its pH. So they want the pH. Now we say that sodium hydroxide is a strong base, and like strong acids, strong bases completely ionizes into sodium ions and OH ions. This is a strong base. And when it dissociates completely into sodium ions and OH ions, which means that if we started with 0.1 mole per decimeter cube of sodium hydroxide, this means that we are going to get also 0.1 mole per decimeter cube of the hydroxide ion. So this is the concentration of the hydroxide ion, equals 0.1. But they do not want the concentration of OH ions, they want the pH. So what are we going to do? We are going to say that 1 times 10 to the power minus 14 equal the concentration of the hydrogen ions times the concentration of the OH ions, which means that the hydrogen ion concentration equal 1 times 10 to the power minus 14 divided by the concentration of the OH ions, which is 0.1. And so we get 1 times 10 to the power minus 13 moles per decimeter cube. So we just used the rule that says that the Kw is equal to the hydrogen ion concentration times the OH ion concentration. We know the concentration of hydroxide ion from sodium hydroxide. And so we can get the hydrogen ion concentration equal the Kw divided by the concentration of the OH ion. We get the concentration of hydrogen ion. Then we say that pH equal minus log the hydrogen ion concentration, which is equal to minus log 1 times 10 to the power minus 13. And this gives a pH of 13, which is predicted because sodium hydroxide is a base, is a strong base. And we said that bases have pHs above 7. And as long as sodium hydroxide is a strong base, then its pH is high, between 12 and 14. Okay? Understand this, or shall I repeat it?
Must repeat one more time, please.
Okay. Here they said that we have sodium hydroxide. We have a solution of sodium hydroxide with this concentration, 0.1 mole per decimeter cube sodium hydroxide. They say find out its pH. Now, in the first thing we are going to do is that sodium hydroxide is a strong base. What does a strong base do? It completely ionizes into sodium ions and OH ions, isn't it? Which means that if we started with a 0.1 mole per decimeter cube of sodium hydroxide, so how much are we going to get as a concentration of the OH ion?
0.1.
0.1 is going to be the same because it's completely dissociated. So all its concentration is converted to OH ion. So the concentration of the OH ion is 0.1. Now, from the previous page, we said that we have a law that says that Kw equals the concentration of hydrogen ion times the concentration of the OH ion. And we said that the Kw was found by scientists to be equal to 1 times 10 to the power minus 14 at room temperature. Okay, so we are going to use this law. We know the Kw, we know the concentration of OH ions, so we can get the concentration of the hydrogen ion. That's what we did here. Kw equal the concentration of hydrogen ion times the concentration of OH ions. We know the value of Kw to be 1 times 10 to the power minus 14. If you do not know it, then you will find it at the data booklet in the first page. But because we are going to solve as many problems as we can, then the Kw is known. It's 1 times 10 to the power minus 14. And we know the concentration of OH ions, it's 0.1. So we substitute for it by 0.1. So the hydrogen ion concentration equal 1 times 10 to the power minus 14 divided by the concentration of the OH, which is 0.1. So we get 1 times 10 to the power minus 13. The pH equal minus log the hydrogen ion concentration. So you write on your calculator minus log and put between brackets 1 times 10 to the power minus 13. You're going to get the pH value 13. Understand?
Yes, miss. Understand.
Okay. We said that the Kw has a value of 1 times 10 to the power minus 14 at room temperature. But as we've seen last time, that the value of Kw differs by the change in temperature. Differs by the change in temperature. As temperature increases, the Kw value also increases. Why does the Kw increases as the temperature increases? And this question usually comes in exams about the value of Kw. Why does it increase by increasing temperature? Because water dissociates into hydrogen ion and OH ion. And this dissociation is an endothermic process. It is an endothermic process, which means that it needs temperature. In endothermic processes, endothermic reactions always are favored by higher temperatures. The more you give it temperature, the more the reaction goes in the forward direction. By increasing temperature for any endothermic reaction, increasing the temperature will shift the reaction towards the formation of more products. So as we increase the temperature, we said that Kw, or the K value, equal the concentration of hydrogen ions times, okay, let's say Kw. We said that Kw equals the concentration of hydrogen ions times the concentration of OH ions. So what happens when we increase the temperature for this endothermic reaction? What happens?
When you increase what?
When we increase the temperature, what will happen for this reaction?
The reaction will shift.
Yes, shift where?
To the other side.
Which side?
Right side.
the right-hand side, isn't it?
Yeah.
When we
Yeah.
increase the temperature, the reaction will shift towards the right-hand side, which means to more concentrations of hydrogen ions and OH ions. So Kw will increase. When we increase the temperature, the Kw increase. Why? Because the dissociation of water is an endothermic process, and endothermic processes are favored by high temperatures, which means that the water will dissociate into hydrogen ions and OH ions. When we increase the temperature, the reaction will go towards the right-hand side because it's favored by high temperature, which means that the concentration of hydrogen ions and OH ions will be high. And so the Kw will also increase. Do you have any question here? Okay, but the water will still have a pH of 7. The water will still have a pH of 7, although the Kw changed. Although the Kw increases by increasing temperature, yet the water will always be neutral. It will have a pH of 7. Why? Because even if the concentrations of hydrogen ions and OH ions increases, yet they are still the same. They are still equal, I mean. The concentration of hydrogen ions and the concentration of OH ions are still equal, which makes water always neutral, having a pH of 7, because both of them are equal. So the water becomes neutral as it is. Understand till here?
Yes, ma'am.
Okay. I don't know if this is all what we took last time or there is something else. Okay, here, this is the dissociation of water. Here, as I told you, the Kw, its value increases as temperature is increased because it is an endothermic reaction. So the more we use, the more temperature, the Kw value will increase. Now we have another term which is called pKw. We said that the letter P means minus log. And we use it because we said that the concentrations or the Ka values are very, very small. As you see here, the values, Kw values are very small, 10 to the power minus 15 or 10 to the power minus 14. So in order to get bigger values, then we take the minus log or the P. pKw equal minus log Kw. So we will see that as we took in case of acids, we said that the more the value of Ka, if you remember this table, we said that the more the value of Ka means that it's a stronger acid. It means that if we compare weak acids, all these are weak acids: propanoic acid, ethanoic, benzoic, methanoic, chloroethanoic, dichloroethanoic, trichloroethanoic acid. All these are weak acids. All these have Ka values. We said that whenever we have a Ka value, this means that we are having a weak acid, having dissociation constants. But if we compare propanoic acid with trichloroethanoic acid, we will find that the value here for Ka is 1.35 times 10 to the power minus 5. And the value for Ka of trichloroethanoic acid is 2.24 times 10 to the power minus 1. It means that this value is much greater than this value, which means that as the acid becomes more stronger, the Ka value becomes greater. The more the value of Ka, the stronger is the acid. But the pKa, as P is minus log, so as if we are taking something opposite, we will find that the opposite takes place. The less the value of pKa, the greater or the stronger is the acid. The more the value of Ka, the stronger is the acid. And the lower the value of pKa, the stronger is the acid. Okay, do you have any question here? Okay, this is also the case in case of Kw and pKw. Here, as the temperature increased, the Kw also increased, but we will find that the pKw will decrease as the temperature increases. Okay. Now here, as I told you, when we take, if they told us that a sodium hydroxide solution of concentration 0.1, then find the pH of the solution. So we solved this problem from a moment. Let's solve another one. It says here, what I didn't mention is also that if they give us the pH and they ask about the hydrogen ion concentration, for example, if they say that the pH of a solution is 2.37, for example, any number, and they say find out the hydrogen ion concentration. So we said to find out the concentration of hydrogen ions, we take 10 to the power minus the pH. 10 to the power minus the minus, we put a minus sign, and then 2.37. At once we are going to get the value of the hydrogen ion concentration. Okay. Now here in this example, it says calculate the pH at 298 Kelvin of an aqueous solution of potassium hydroxide of concentration 0.02, and they gave us the Kw value to be 1 times 10 to the power minus 14 mole square decimeter minus 6. Now, potassium hydroxide, like sodium hydroxide, it's a strong base, and it means that it completely dissociates into potassium ions and OH ions. So can you solve this problem? What am I going to write below potassium hydroxide or below potassium ions and OH ions?
We're gonna write the concentration of them.
Yes, what is the concentration of potassium hydroxide in our problem?
0.02
Yes, excellent. Which means that the hydroxide ion concentration is also?
will be the 0.02.
Yes, excellent. So what are we going to calculate here?
We want to calculate the, yeah, so we're gonna have to find Kw first.
Yes, they said that Kw equal 1 times 10 to the power minus 14. We want to calculate pH. What is pH?
pH is a negative log times the concentration.
Concentration of what?
OH.
No, of hydrogen ion concentration.
Oh, hydrogen positive, yes.
This is pH. So it's minus log the hydrogen ion concentration. Do we have the hydrogen ion concentration?
No.
No. So how do we get it?
We will have to do, we will have to, 1 second.
Yes.
We will have to use the Kw.
Yes.
And divide it by the concentration of OH minus, which is 0.02.
Yes, excellent. So we will write 1 times 10 to the power minus 14 divided by the concentration of the OH, which is 0.02, to get the value of the hydrogen ion concentration. They said that this value equals 5 times 10 to the power minus 13. After we get the hydrogen ion concentration, we say that the pH equal minus log
negative log times 5 times 10 to the power negative 13.
Yes, and we get the pH, excellent, to be 12.3. Okay. Now, this is a method. Here we have another method to do. Yani this method is completely correct, but there is another way to solve such a problem. Now, we said that Kw equal the concentration of hydrogen ion times the concentration of the hydroxide ion. Now, the other way is that to take the minus log of both sides. We say here minus log Kw equal minus log hydrogen ion concentration minus log OH ion concentration. We are going to take minus log both sides. And from log properties, if we have two values times each other, we take minus log the first plus minus log the second. Here there is a plus. Okay. This is from the properties of logs, that if we have two values multiplied together, if we take the log of them, we add them together. We take minus log the first plus minus log the second. Okay. So we took minus log both sides. Minus log Kw equal minus log hydrogen ion concentration plus minus log the OH ion concentration. And we said that minus log, we are going to write it as P. So pKw equals pH plus POH. Okay, you understand how I got this rule?
Yes.
So pKw equal pH plus POH. pKw means that we are going to take minus log Kw, which is 1 times 10 to the power minus 14, which is equal to 14. So instead of pKw, I'm going to write 14 equals pH plus POH. This is the rule that we can use. You can use the other rule or this rule. They are both correct. Now, when they said that we have potassium hydroxide with a concentration of 0.02 moles per decimeter cube, and they want us to find the pH of the solution. So what we are going to do here is to calculate the POH of the hydroxide ion. We know that the hydroxide ion equals 0.02. So POH means minus log 0.02, which is equal to minus log 0.02, which is equal to 1.6989, means 1.7, approximately 1.7. It's 1.69897. So approximately it's 1.7. Okay, so this is the POH. We took the concentration of the hydroxide ion. We got its POH, means minus log the concentration of the hydroxide ions. It was about 1.7. So we say that the pH equals, from this rule, the pH equals 14 minus the POH, which is 1.7. And so we get 14 minus 1.7, we get 12.3. We just substitute in this rule that instead of saying Kw equal hydrogen ion concentration times OH ion concentration, so we say that the hydrogen ion concentration equals 10 to the power minus 14 divided by 0.02, and we get the hydrogen ion concentration and then get its pH. We can do an alternative method that we say that 14 equal pH plus POH, from which we can get the pH directly. At the beginning, we get the POH, which is minus log the OH ion concentration. We get its value. And then the pH equals 14 minus the POH, we get the pH directly. Either you do this or you do that, both are correct. But do you understand this second method, or shall I repeat it?
Yes, they're both fairly easy,
Okay.
no difference.
Yes. Okay. Now we come to analyzing data from the pH measurements. What do we mean by analyzing the data? It means that we can determine whether our acid is a strong acid or a weak acid from the pH values. We know that whenever we have a lower pH value nearer to 0, this means that we have a very strong acid. And as we go further away from the 0 value till the 7, this means that our acid becomes weaker. So here we have a very strong acid in this area from 0 up to 2 تقريبا, and from 2 to 7 we have a weak acid, weaker acids. Of course, the more we come nearer to the 7, the more will be a weaker acid. So here from the value of the pH, we can determine whether our acid is strong or weak. Or we can compare between two strong acids with whether, or between two acids, whether they are compared to each other, which one of them is stronger than the other. Of course, we have to do this comparison at the same temperature, because we've seen that that the Kw value differs by changing the temperature. So here, if we are using all solutions of 0.1 mole per decimeter cube of, we take solutions of hydrochloric acid, dichloroethanoic acid, monochloroethanoic acid, ethanoic acid. Sorry, this is methanoic, this is ethanoic, and this is propanoic acid. So if we take all the solutions having the same concentration and we measure their pH at the same temperature, which is 298 Kelvin, we will find that the pH of HCl is 1, of dichloroethanoic acid is 1.14, of chloroethanoic acid 1.93, methanoic acid 2.38, ethanoic 2.87, and propanoic acid 2.93. We will find as the pH increases, this means that the acid becomes weaker. This means this is the smallest value for pH, and we said that smaller values for pH means stronger acids. So HCl is a stronger acid than dichloroethanoic acid, which is stronger than monochloroethanoic acid. Here, methanoic and ethanoic, also we have ethanoic stronger, methanoic acid is stronger than ethanoic acid, which is stronger than propanoic acid. And of course, we are going to study this afterwards in organic. We are going to study why dichloroethanoic acid is stronger than the others, why methanoic acid is stronger than ethanoic and propanoic. So as we go to the right-hand side, the value of the pH increases, which means that we get weaker acids. The more the value of pH, the weaker is the acid. And also we can do the same in case of bases. If we compare the pH values of bases, we said that bases range in their pH values from 7 to 14. So the more we approach the 14, the more will be the base stronger. The stronger will be the base. For example, if we compare ammonia, also we are going to take the same concentrations of different bases, 0.1 mole per decimeter cube, and we are going to measure their pH at 298 Kelvin. We will find that, for example, if we compare ammonia, which is 11.13, and compare it with sodium hydroxide, which is 13, we will see that the more the value of the pH, the stronger here will be the base. The stronger sodium hydroxide is more stronger than propylamine, more stronger than ethylamine, and so on, till at the end we get the weakest base here is ammonia. So from the pH value, we can determine whether we have a strong acid or a strong base, or a weak acid or a weak base, and we can compare the strengths of acids and bases together from the value of pH. Also, if we look here at salts, if we take salts, we will see that not all salts have a pH of 7. We'll find that some of the salts have a pH of 7, like sodium chloride, potassium nitrate, and ammonium ethanoate, but others do not have a pH of 7. It could be greater than 7, which means that our salt is basic, or less than 7, which means that our salt is acidic. Now, how can we know that the pH of the salt will be 7 or not? Now, if we look at sodium chloride, for example, we know that a salt is formed We know that a salt is formed by reacting an acid with a base. So sodium chloride comes from sodium hydroxide and HCl. We divide the salt into two and see from where does the cation come from. Usually cations come from bases and anions come from acids. So we are going to put a line here and see the cation comes from which base and the anion comes from which base, from which acid. So sodium comes from sodium hydroxide and chloride comes from hydrochloric acid. Now, is sodium hydroxide a strong or a weak base? Sodium hydroxide, is it a strong or a weak base?
It's a strong.
It's a strong base, yes. What about HCl?
It's a weak base.
No, HCl. HCl is a base?
No, it's an acid.
So what is its strength?
It's a strong acid.
It's a strong acid. So when we have a strong base and a strong acid reacting together to give a salt like sodium chloride, strong and strong, so no one wins. And this means that the pH of sodium chloride will be 7 because both of them are strong. This means that neither of them will predominate on the other. And this means that the pH of the salt will be 7. What about potassium nitrate? How will we know that its pH is 7 as is written? What are we going to do?
Same thing, I think.
Okay, same thing. So what are we going to do? I want you to answer. I know that it's same thing. So what are we going to do to know its pH is 7?
Unless you want to calculate?
No, just as I did
same
here.
thing? Okay, we're gonna write that whether it is a strong or weak base or acid.
Yes. So what are we going to do? We said we are going to put a line here to divide the positive ion from the negative ion. From where does the potassium ion comes from?
From
the positive ions always come from a base. What is the base that we took from it the potassium ion? Which base reacted with the acid to give potassium nitrate?
I don't know.
It's potassium hydroxide. This is the base, potassium hydroxide. When you react potassium hydroxide with what?
Potassium hydroxide and HNO3.
What is NO3? We don't have an acid called NO3.
HNO3.
HNO3, which is called nitric acid. So if you react potassium hydroxide with nitric acid, you get potassium nitrate plus water, isn't it? So the salt comes, this is the salt. The salt comes from the reaction of a base with an acid. Potassium hydroxide reacting with nitric acid. Now, is potassium hydroxide a strong or a weak base?
It's a strong base.
Yes, it's a strong base, just like sodium hydroxide. Both of them are present in group 1. Sodium and potassium, both of them belongs to group 1. So their hydroxides are strong bases. What about nitric acid?
Strong acid also.
Yes, it's also a strong acid. So strong base reacting with strong acid, no one wins. Both of them are strong. No one predominates. And so it has a pH of 7. Okay, since no one predominates, no one is stronger than the other, then the pH is 7. Now let's look at the third salt, sodium ethanoate, CH3COONA. From where does its ion come from? Where shall we put our line?
Between OO and Na.
Yes, excellent, here. So This is the ethanoate ion. From where does ethanoate ion come from?
CH3COOH.
Yes, the ethanoic acid. Excellent. And the sodium comes from where?
It comes from NaOH.
Sodium hydroxide. Now, sodium hydroxide, is it a strong or a weak base?
Sodium hydroxide is a strong base.
Yes, it's a very strong base. It's the strongest base. Itself and potassium hydroxide are very strong bases. What about ethanoic acid?
It's a weak acid.
Yes, excellent. It's a weak acid. So we have a weak acid reacting with a strong base. Which one will predominate?
The strong base.
Yes, excellent. So we'll say that the salt altogether will be a base. That's why its pH is greater than 7. Of course, we don't have to know that it's 8.88, but we know that sodium ethanoate, as it comes from a strong base and a weak acid, this means that its pH should be greater than 7 because the hydroxide is stronger, the base is stronger than the acid. So the salt formed will be a base. Now, what about ammonium chloride? It comes from what? What is the chloride coming from what?
HCl.
Yes, it comes from HCl. What about ammonium? The ammonium ion comes from
it
ammonia.
Comes from NH3. That's it.
Yes. So ammonia, is it a weak or a strong base?
It's a weak base.
Yes, excellent. And what about HCl?
It's a strong acid.
Yes, excellent. So here we have a strong acid and a weak base. So which one will predominate?
Yeah.
It's the strong acid, and this means that the ammonium chloride salt is acidic. It has a pH lower than 7. It's acidic. So it depends on the ions that the salt comes from.
It depends on who predominates
Yes.
to predetermine its pH, whether it's going to be acidic,
excellent.
neutral, or basic.
Yes, excellent. So if both are strong, we have seen that the pH is 7. If one of them is stronger than the other, then the stronger will predominate and will determine whether our salt is a base or an acid. Now, if we look at this last one, the ammonium ethanoate, which is CH3COONH4, we said that we are going to put a line between the positive ion and the negative ion. Now, from where does ammonium ion comes from?
Ammonium ion comes from ammonia itself.
Excellent, from ammonia. What about ethanoate ion comes from?
It comes from CH3COOH.
Yes, ethanoic acid. Excellent. Now, we said here that ammonia is a weak base and that ethanoic acid is weak or strong?
It's a weak acid.
Yes, excellent. It's a weak acid. So here we have both of them weak. Ethanoic acid is a weak acid and ammonia is a weak base. Does any one of them
none of them predominate, no, so
yes.
it would be neutral.
Yes, excellent. Neither of them predominated. That's why ammonium ethanoate has a pH of 7. But of course it's 7 because when we have a weak acid, we said that it has a Ka value. And also if we have a weak base, it has something called Kb. It's like the Ka. We are not going to deal with it in our studies, but the Kb measures the strength of the base as the Ka measures the strength of the acid. So when we look at the Ka value, which is the acid dissociation constant of ethanoic acid, we find that it has the same value as the Kb of the ammonia, the basic dissociation constant of ammonia. It measures the strength of ammonia. So both are equal. And since both are equal, we got a pH of 7. We got the ammonium ethanoate as neutral. But sometimes when we are dealing with weak and strong bases, like here, when you see here in this table, you will find that sometimes the Ka value of the weak acid is greater than the Kb value of the weak base. And in that case, we will find that the pH will not be equal to 7, like in case of ammonium ethanoate, but it comes less than 7, because the Ka value of the weak acid is greater than the Kb value of the base. And if we are here dealing with weak acids together with weak bases, it depends on their Ka values. For ammonium ethanoate, here we have found that both ammonia, Kb of ammonia and Ka of ethanoic acid were equal. That's why ammonium ethanoate has a 7, pH 7. But sometimes in other weak salts coming from a weak acid and a weak base, we will find that the Ka value is greater than the Kb value. So the pH of the salt will be less than 7. And if the Ka value is less than the Kb value, then the pH will be greater than 7 for the salt. Okay, do you have any question here? Okay, now let's see what is the effect of dilution on the pH of aqueous solutions of acids. If we take strong acids, if we take a strong acid, for example, hydrochloric acid, and we are going to take different concentrations of this hydrochloric acid. We are going to take a concentration of 1 mole per decimeter cube of hydrochloric acid, and then we are going to dilute it by a factor of 10 times to be 0.1 mole per decimeter cube, and then diluted more by a factor of 10 to be 0.01 mole per decimeter cube, 0.001, here it should be 0.0001, 3 zeros before the 1, because it's written here 10 to the power minus 4. So we are diluting each time the acid by a 10-fold. And then we are going to measure the pH of each solution at 298 Kelvin. We will see that if we dilute the acid, the strong acid, here we are dealing with strong acids like HCl. If we dilute it 10 times, we will find that the pH value will differ by 1. If we started with HCl having a concentration of 1 mole per decimeter cube, it's a high concentration, we find that the pH is 0. Minus log 1 is equal to 0, so the pH is 0. If we take a diluted solution by 10 times of the first, 0.1 mole per decimeter cube, if we calculate the pH is minus log pH equal minus log 0.1, we get a 1 value. If we diluted more to 0.01, we get a value of 2, pH equals 2, 0.001, 3, 0.0001, 4. So as we can see here, that by diluting the acid, the strong acid, by 10-fold, the pH value will differ by 1 unit each time. But of course, we will see that if we reach a value of 10 to the power minus 8, then this will mean, according to this, to what we were doing, that the pH will be equal to 8. Understand what I mean? We are diluting 10-fold, 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 10-fold. Here we reach 10 to the power minus 4. What happens if we dilute it to 10 to the power minus 8? It is a strong acid, HCl. If we dilute it to 10 to the power minus 8. So if we want to calculate the pH, we will find it to be 8. And of course, this is nonsense, because we don't have an acid having a pH equals to 8. So why do we get this number? We get this number because when we calculated the pH, we didn't consider that water is present in our solution. That water itself has a factor of pH equals 7 that will affect the ionization of water, will affect the ionization of the acid. We didn't put it in our consideration. That's why we will not say that if we have a concentration of 10 to the power minus 8, that the pH will be 8. No, we are not going to say such a thing, because this will be nonsense, because this is an acid. Its pH couldn't be 8. So that's why we will say that if we have an acid having a concentration of 10 to the power minus 8, then the pH will be close to 7. It will be less than 7, but very close to 7, because it's a very dilute solution of an acid. So it became very close to a neutral solution, because the pH of water is 7. And during our calculations for pH, we didn't put the concentration or the dissociation of water into our consideration. Of course, we are not going to put it in our consideration, but I just wanted to tell you that if we have a concentration that is very, very dilute of a strong acid, this doesn't mean that the pH is basic. No, it will be close to 7. Okay.
Yes, ma'am.
Okay, what if we make dilution to a weak acid, not a strong acid? If we take, for example, ethanoic acid, which is a weak acid, and we start with a concentration of 1 mole per decimeter cube of ethanoic acid, and then we start to dilute it 10 folds or 10 times. So for the 1 mole per decimeter cube concentration of ethanoic acid, if we measured its pH at 298 Kelvin, we found it to be 2.38. Now we are going to dilute this solution 10 times to get it 0.1 mole per decimeter cube instead of 1. We will find that the value of the pH will be raised by 0.5, not 1 unit as in case of the strong acid. No, it's going to be raised by only 0.5, because this is a weak acid, not a strong one. If we dilute the 0.1 mole per decimeter cube ethanoic acid 10 more times to have a concentration of 0.01 mole per decimeter cube, we will find also that the pH will rise by a 0.5 unit. The more we increase the concentration by 10 times, the more the pH value will increase, but by only 0.5 unit, not 1 unit as in case of strong acids. So strong acids are more affected by dilution, but weak acids, as they are weak, they will not be strongly affected by dilution like in case of the strong acids. Okay. Do you have any question in this part?
No, miss.
Okay, now we come to acid-base titrations, pH curves, and indicators. Of course, this is a very important part in this chapter. You are usually asked about drawing pH curves and determining the indicators that you are going to use. So would you please, Yani, concentrate? And if you have any question, please ask. Now, what are acid-base titrations? We know that when we have an acid with an unknown concentration, for example, we have an acid of an unknown concentration, and we want to determine its concentration. So we say that we are going to titrate this acid with a base of known concentration. To know the concentration, the unknown concentration of this acid, we have to titrate it with a base of known concentration. So in titration, we use a conical flask, and also we use a burette to place our liquids in. So here we have the conical flask at which we are going to place, for example, 50 centimeter cube of, for example, HCl that we do not know its concentration. So in order to know its concentration, we have to titrate it against, for example, sodium hydroxide with known concentration, for example, 0.1 mole per decimeter cube. And by titrating the hydrochloric acid of unknown concentration with the sodium hydroxide with known concentration, and from their volumes, we can determine the concentration of HCl. We do not know the concentration of HCl. But as you know, that both HCl and sodium hydroxide are colorless. HCl is colorless, and also sodium hydroxide is colorless. So if we do have two solutions that are colorless, so when will we know that the reaction stopped? Of course, in titration, we add sodium hydroxide from the burette drop by drop until we get a volume of sodium hydroxide that will neutralize the HCl that is present in the conical flask. We know that sodium hydroxide reacts with HCl to give a salt, which is sodium chloride and water. And this means that sodium hydroxide will neutralize, we call this a neutralization reaction, because sodium hydroxide is a base and HCl is an acid. They will neutralize each other to get salt and water. So if we add sodium hydroxide drop by drop from the burette to the HCl in the conical flask, we add it until the sodium hydroxide completely neutralizes the HCl present in the conical flask. And then we are going to do some calculations in order to determine the concentration of HCl. Now, since HCl is colorless and sodium hydroxide is colorless, when will we know that the reaction stopped? When will we know that we added enough sodium hydroxide to the HCl in order to neutralize it? Can we know?
No, Miss, I was gonna ask you the question.
You didn't hear about titration before? You don't know what we add here in order to know when the reaction stopped? Or when all the HCl reacted with sodium hydroxide? Of course you know. We add something here. You don't remember?
I don't remember.
We add what we call indicators. We took it in O level and we took it in AS. We add what we call an indicator. We have two types of indicators in titrations that are mainly known for us, but of course we are going to take more this year. We took something called methyl orange indicator, and we took another indicator called phenolphthalein, isn't it? Methyl orange in the acid medium has a color of red. In basic medium, it has a yellow color. And in neutral medium, it has an orange color. Phenolphthalein in the acid medium is colorless. In the basic medium, it's pink. You don't remember them even till now?
I do now, Miss.
We add here something called an indicator. What is an indicator? The indicator is a substance that changes its color from the acid medium to the basic medium, and we are going to study why. But let us start with this, that the only definition that we know up till now from O level and AS, that when we add an indicator here, the indicator with the acid has a color that is different than its color with the base. So when we do titrations, we usually add 2 drops or 3 drops of an indicator so that it will have a color with what we are placing in the conical flask. For example, here we are placing hydrochloric acid in the conical flask. If we add methyl orange, then we will see that the color of HCl becomes red. And then we are going to titrate with sodium hydroxide the point at which the indicator changes its color from red to orange, this means that now all the acid present in the conical flask is neutralized by the amount of base added. And then from the volume of HCl and from the volume that came down from the burette of sodium hydroxide, from the volume and concentration of sodium hydroxide, we can determine its number of moles. And we say here, as the mole ratio is 1:1, then the number of moles of sodium hydroxide, now the volume here is known. So we say that N, the number of moles, equal concentration times volume of sodium hydroxide. We know the number of moles of sodium hydroxide, which is equal to the number of moles of HCl in this reaction. And since we know now the number of moles of HCl and we know its volume, we can determine its concentration. Number of moles equal concentration times volume. So we are going to add an indicator to the acid. It has a red color. If we use methyl orange as an indicator, it will have a red color. We are going to titrate using sodium hydroxide until the color of the indicator changes from red to orange. This means that we reached what we call the equivalence point. We reached the equivalence point. What is the equivalence point? The equivalence point is the point at which the volume of sodium hydroxide added completely neutralized the amount of HCl that is present in the conical flask. We call this the equivalence point. The volume of the base added which completely neutralized the acid. This is the equivalence point. So at the equivalence point, when the indicator changed its color, then we say that the number of moles of sodium hydroxide equals its volume times its concentration, and we get the number of moles, which is equal to the number of moles of HCl. And then we say that the number of moles of HCl equal its concentration times volume. We know the volume, which is 50 centimeter cube. We divided by 1,000 to get it in decimeter cube. We know the number of moles of HCl. We can determine the concentration of HCl. Understand the idea of titration?
Yes, miss.
Okay. Now, in this part of our chapter, we don't know which indicator that could be used. We don't know yet which indicator should be used. We have different indicators, not only methyl orange and phenolphthalein. We have different types of indicators. So in this part of the chapter, we are going to deduce which indicator to use in our titrations. So if we want to determine which indicator to use, we have to study first what we call pH curves. pH curves or titration curves, and from which we can determine which indicator to use in our titration. So here we are going to study first the acid-base titrations, or we call them the pH curves, so that from these pH curves, we can determine which indicator to be used afterwards in our reactions or in our titrations. Now, at the beginning, we should differentiate between something called the end point and another point, which we call the equivalence point. Now, what is the end point? We said that the indicator will change its color. In the acid medium, we'll have a certain color, which is different from the color in the basic medium. So the volume, or the pH range, or the pH at which the indicator changes its color from the acid medium to the basic medium, we are going to call it the end point. So the end point, is the pH at which the indicator changes its color. Change its color. We call this the endpoint. So the endpoint is the pH at which the indicator changes its color. There is a certain pH for every indicator at which this indicator changes its color, and we are going to see how do we know it. Okay, but what is the equivalence point? The equivalence point is when the acid and the base have reacted together in exact proportions as dictated by the stoichiometric equation. So when we reacted HCl with sodium hydroxide, so the equivalence point is the volume of one of them that is needed to completely neutralize the other, as indicated in this equation, because here the number of moles are equal. But if we take sulfuric acid reacts with 2 moles of sodium hydroxide to give the salt, which is sodium sulfate. If we balance the equation, we will see that the mole ratio between sulfuric acid to sodium hydroxide is 1:2. So it's the volume of sodium hydroxide or the volume of HCl that completely neutralizes the other according to their mole ratio. So there's a difference between the endpoint and the equivalence point. The endpoint is the pH at which the indicator itself changes its color. But the equivalence point is related to the solutions that we are working with. It is the volume of one of them that completely neutralizes the other according to their mole ratio. Understand me, or shall I repeat this?
No, I understood.
Okay, so there's a difference, but maybe sometimes when we are working, sometimes when we titrate an acid with the base, we say the end point is so and so. We don't say the equivalence point, we say the end point. This is not very correct, but we will see that there is a relation between them. But it's not correct to say the end point. It should be said the equivalence point. But usually we say end point, okay? But there's a difference between them. Now, how can we choose our indicator? As we said, we are going to study the titration curves and see which indicators we are going to use in each type of titration. So let's start with a titration of strong acid with a strong base. We are titrating, for example, hydrochloric acid with sodium hydroxide. So here we are not going to put our solutions in a conical flask, because here we are not going to use an indicator. We don't know which indicators to be used yet. So we are going to get a beaker and place a certain volume of, for example, the acid. Maybe we are going to place, for example, 50 centimeter cube of hydrochloric acid of known concentration. Now here we are going to use both solutions with known concentration, for example, 1 mole per decimeter cube. And what we are going to do here is to make the titration using a pH meter. We are going here to use a pH meter instead of the indicator to determine the equivalence point. So the pH meter, as you see, consists of an instrument at which a reading is shown here. And we have an electrode, or we call it a probe. We place it in our solution. When we place this electrode in our solution, at once a reading is shown on the screen here. So when it showed a 3.2 pH 3.2, this means that our solution is acidic. We started with an acidic solution having a pH of 3.2. Now we are going to titrate, or we are going to put a burette here. And in this burette, we are going to fill it with sodium hydroxide, also having the same concentration of 0.1 mole per decimeter cube. Now here, both solutions, we know their concentrations, because in this titration, we do not want to know the concentration of one of them. No, We are searching for the indicator to be used in this titration. Which indicator should we use? Should we use methyl orange? Should we use phenolphthalein? Should we use other indicators like, for example, phenol blue or bromothymol blue or methyl red? We have a lot of indicators. Which one can we use? So we bring a beaker, place a 50 centimeter cube of HCl of known concentration in this beaker, and measure its pH value by a pH meter. And then we fill a burette with sodium hydroxide with the same concentration, which is 0.1 mole per decimeter cube. And we are going to add drops of sodium hydroxide to our solution. And at every 1 centimeter cube or less, we are going to read the pH reading. Understand what we are going to do?
Yes, miss.
You understand, or shall I repeat it?
No, miss.
Okay, so let's see what happens. Now here, as we said that we started, here they started with sodium hydroxide. This is not, of course, if they started with a solution that gives 3.2, this means that it's acidic. But here in this graph, they started placing in the beaker, they placed sodium hydroxide instead of HCl. They placed here about 25 centimeter cube of sodium hydroxide, and they are going to titrate it with HCl, hydrochloric acid, is strong. We are titrating a strong acid with a strong base, and we are measuring the pH of the solution using the pH meter. So they started with 25 centimeter cube of the strong base sodium hydroxide. We know that sodium hydroxide is a strong base, and this means that its pH range between 13 and 14. So they started with a pH of 14. Okay, pH 14 means that we started with a solution of sodium hydroxide. Now we are going to add drops of HCl. When drops of HCl are added to the sodium hydroxide, then part of the sodium hydroxide present in the beaker will react with the drops of HCl that are falling down from the burette. Sodium hydroxide reacts with HCl, forming the salt, sodium chloride, and water. But part of the sodium hydroxide only reacted, and the other part still is present in the form of sodium hydroxide. When we added 1, 2, 3, 4, 5, 6, 7, 8, and so on milliliters of HCl to sodium hydroxide, every centimeter cube that we added from HCl reacts with only part of the sodium hydroxide to form the salt and water, but the rest of the solution is still in the form of sodium hydroxide. That's why here we are drawing a pH, the pH against the volume of the acid added. When we started with sodium hydroxide, its pH is 14. And as we add HCl to the solution, we will see that the pH value does not change, or we say that it changes gradually as more and more of the acid is added, until we have added nearly about 24.5 centimeter cube of HCl. This is near the equivalence point, because since both acids have the acid and the base have the same concentration, this means that, and as they are reacting in a 1-to-1 mole ratio, they have the same concentrations and they are acting in a 1-to-1 mole ratio. So this means that the volume at the equivalence point of the acid should be equal to the volume of sodium hydroxide that we started with. We started with 25 centimeter cube, and this means that the equivalence point should also be at the addition of 25 centimeter cube of the acid. Understand why?
No, miss, one more time.
Okay. We are reacting sodium hydroxide plus hydrochloric acid to give sodium chloride plus water, isn't it? We started with 25 centimeter cube of sodium hydroxide having a concentration of 0.1 mole per decimeter cube. Now we are titrating with HCl of 0.1 moles per decimeter cube as well. So what will be the volume of HCl needed to reach the equivalence point? What is the equivalence point? It is the point at which the number of moles of sodium hydroxide is equal to the number of moles of the acid. This is what we call the equivalence point. It is the point at which a certain amount of sodium hydroxide is completely neutralized by the acid added. So we want to know what is the amount of sodium hydroxide that is present in our beaker here when we used 25 centimeter cube of sodium hydroxide having a concentration of 0.1 mole per decimeter cube. So we will see that the number of moles of sodium hydroxide equal concentration times volume, equal its concentration times the volume that we started with, 25 divided by 1,000. We get a number of mole of 0.0025. Okay, this is the number of moles of sodium hydroxide. What will be the number of moles of HCl?
Miss, we have the it's concentration.
Okay.
We want to find the number of moles of HCl.
Yes.
Don't we have to multiply concentration by volume? But we don't have a volume.
Okay, so what we are going from, where do we get the number of moles of HCl? We did a lot of these calculations in the
ratio.
Yes, from the Mohr ratio. Excellent. From the Mohr ratio here, the Mohr ratio is 1:1. So what will be the number of moles of HCl?
It's going to be the same, 0.0025.
Yes, it's going to be the same. So the number of moles of HCl is the same. Now we got the number of moles of HCl and we got its concentration. So what will be its volume? How can we calculate the volume of HCl?
Volume over volume equals number of moles over concentration.
Yes, excellent. So it's going to be 0.0025 divided by its concentration. So we get a volume of 0.025 decimeter cube, 0.025 decimeter cube, or else 25 centimeter cube, isn't it?
Yes.
So this means that if we start with the same concentration of both solutions, and since they are reacting in the Mohr ratio 1:1, then their volumes will also be equal at the equivalence point. The equivalence point, we said that it is the volume at which a certain amount of the base is completely neutralized with the acid. So if the base and the acid have the same concentration and they are reacting in the Mohr ratio 1:1, then the equivalence point will be the volume of HCl added to neutralize the sodium hydroxide is going to be equal to that of the sodium hydroxide. Isn't it?
Yes, ma'am.
So this means that if I'm titrating this sodium hydroxide, 25 centimeter cube, I'm titrating it with HCl. And I'm using the same concentration of HCl as that of sodium hydroxide, which is 0.1 mole per decimeter cube. This means that to reach the end point, the volume of HCl should also be 25 centimeter cube And we did it by calculations. You see that by calculations, we got the same volume since we started with the same concentrations. This means that the equivalence point will have the same volume. Okay. The equivalence point will be the volume of HCl needed to neutralize the 25 centimeter cube of sodium hydroxide, which is equal also to 25 centimeter cube HCl, because we started with both of them having the same concentration, and they are reacting in the mole ratio 1:1. Understand me?
Yes.
Okay, so here in this curve, you see that we started with sodium hydroxide in our beaker. This is the first thing that you have to notice, that we started with sodium hydroxide. This means that the pH that we are going to start to draw our pH curve with, that we should choose 14, because it's a strong base. It's a very strong base. Okay, now we are going to add HCl from the burette, having the same concentration. This means that our equivalence point will be also 25 centimeter cube, because we started with 25 centimeter cube of sodium hydroxide. So the equivalence point is the volume of HCl that will completely neutralize this 25 centimeter cube. It will also be 25 centimeter cube of the acid added. Understand why?
Yeah, miss. Now.
Yes or no?
Miss. Now I understand.
Now you understand. Okay. Now, as we are adding HCl to the sodium hydroxide, every centimeter cube that we add from the acid neutralizes part of the sodium hydroxide in the beaker. And when we measure the pH using the pH meter, we'll find that there is a very small gradual change in the pH of sodium hydroxide as more and more HCl is added. Because any HCl added to the sodium hydroxide will form sodium chloride and water. But the rest of the solution is in the form of sodium hydroxide. That's why the pH does not change except very, very little or very, very slightly, until we reach the volume of about 24.5 centimeter cube of the added HCl. We find that the curve decreases a little bit more, but at 25 centimeter cube exactly of adding HCl to the sodium hydroxide, we reached the equivalent or the equivalence point, the point at which the acid added, the volume of the acid added, completely neutralized the sodium hydroxide that is present in the beaker. At this point, we'll find that there is a sharp drop in the pH will take place. A sharp drop happens in this part from about pH 11, approximately from about pH 11 to about pH 3. There is a sharp drop happening here in pH. As long as we were adding HCl to our solution, we said that part of sodium hydroxide reacted with the HCl, but most of the solution present, or the remaining of the solution present, is present as sodium hydroxide having high pHs. After the equivalence point, if we add more of HCl, now all the sodium hydroxide reacted, and any volume in excess of HCl that comes down here in the beaker will make the beaker acidic, and the pH will change to be acidic. So in this part, we have only HCl present. All the sodium hydroxide had already reacted. And in this part, mainly we have sodium hydroxide, because any HCl added to the sodium hydroxide would give us the neutral salt, which is sodium chloride, and water, which is also neutral. And the remaining sodium hydroxide is the one having the pH that we see here. At the equivalence point, when we added 25 centimeter cube of HCl to the 25 centimeter cube of sodium hydroxide, this means that all the sodium hydroxide will completely react with the 25 centimeter cube that we added with from the acid. And this means that we only have a neutral solution. And we will see that the pH will drop sharply from about 11 to about 3. It drops sharply. Any extra drop added from HCl will make the solution here acidic. That's why we will find that the pH will drop to 1. Will drop to 1 as the solution becomes acidic. Understand what's happening, or shall I repeat it?
Understood.
Okay, so this sharp drop happens within the range of adding 24.5 centimeter cube of the acid and a little bit after it. But at 25 exactly, we have this sharp drop. You should know how to draw the pH curves. They will ask you in the exam to draw a pH curve. Of course, it depends whether you are starting with an acid or a base, and whether it is a strong or a weak acid or a weak and strong base. So in our case here today, we are studying the titration of a strong acid with a strong base. We started with the strong base, so the pH is 14. We are titrating with HCl, so we draw here on the x-axis the volume of the acid added in centimeter cube. The pH will nearly remain constant. It changes very, very gradually, very, very slightly, until before the end point by only very, very about 0.5 centimeter cube of the acid added, you will find that there will be a change and then a sharp drop at exactly the equivalence point where the volume of the acid is equal to the volume of the base. There will be a sharp drop, and then any more HCl added will make the solution acidic. That's why we will find that the pH will then drop to about 1 or between 0 and 1. Okay, so this is the shape of the pH curve upon the titration of HCl with hydrochloric acid. As they said here, that the steep plunge or the steep drop will take place from 11.3 pH, 11.3 to 2.7, about 2.7. So also you have to know these values, nearly from 11 to 3. So you have to know this value because you are going to make your drop in this pH range. Now, since here, when we reacted HCl with sodium hydroxide, the salt sodium chloride was obtained together with water, and we just studied that the pH of sodium chloride is 7, as it comes from a strong acid with a strong base, the pH is 7. So you will find that our equivalence point, we take the pH 7, which is half the way from 11 to 3. If you make 11 minus 3, so you get how much? 7. So divide
No,
7.
miss, you get 8.
8, okay, 8. So you divide it by 2, you get 4. So from 3 plus 4 makes 7. So that's why the pH is 7. At the end point or at the equivalence point, the pH will be equal to 7, as sodium chloride is a neutral salt. The pH will be 7. The midway from the maximum pH to the least pH, the midway is at pH 7. Okay, understand? Because you are going to be, they are going to ask you to draw such curves. Is there anything that you do not understand?
No.
Okay. Now, we can take another titration curve, the titration between a weak acid and a strong base. Now, here we are going to start with the strong base, which is sodium hydroxide. We are going to take 25 centimeter cube of sodium hydroxide and react them with 0.1 mole per decimeter cube concentration of sodium hydroxide. We reacted with a weak acid, which is ethanoic acid, having the same concentration, 0.1 mole per decimeter cube. And also in this reaction, the ethanoic acid reacts with the sodium hydroxide in a 1-to-1 mole ratio to give sodium ethanoate plus water. So also here, the reaction is 1-to-1, which means that also at the equivalence point, it will need 25 centimeter cube of the ethanoic acid to completely react with the 25 centimeter cube of sodium hydroxide that are present in the beaker. Understand why? It's the same as what we said for HCl with sodium hydroxide. Since the mole ratio is 1-to-1, and since both have the same concentration, this means that the equivalence point will take place at the same volume as that of the sodium hydroxide. Here we started with sodium hydroxide, so we have to start our titration curve at pH 14. This is pH drawn against the volume of the weak acid added per centimeter cube. We started at pH 14 because sodium hydroxide is a very strong base. Now, as we add ethanoic acid to the sodium hydroxide, the salt sodium ethanoate is formed plus water. And we took from some time in this lesson, we took that sodium ethanoate is a basic salt because it comes from sodium hydroxide, which is a strong base, and ethanoic acid, which is a weak acid. So the strong predominates and the salt will be basic. That's why you see that the pH curve does not change its pH as more and more of ethanoic acid is added, because the salt formed is basic and sodium hydroxide is a strong base, so the pH will remain until before 25 centimeter cube by a very small amount. We will see that there will be a small change, and then a sharp drop will take place at the equivalence point, which means that the equivalence point, that means that all the sodium hydroxide, the 25 centimeter cube sodium hydroxide reacted completely with the 25 centimeter cube added from the ethanoic acid. After that, if we add any more ethanoic acid, the solution becomes acidic. But since ethanoic acid is a weak acid, we will see that the pH will not go down as in the case of HCl. We have seen that the pH was lowered till in between 1 and 2. No, here, since ethanoic acid is a weak acid, we will see that the pH will range between 3 and 5. Maximum, it will reach between 3 and 5, because ethanoic acid is a weak acid, not like HCl. In the previous titration curve, we were using HCl. That's why the pH was lowered to in between 1 and 2. Here we are just using ethanoic acid, which is a weak acid. That's why the curve is higher at a pH between 3 and 4. We will see that the equivalence point will take place between pH 8, the equivalence point will be between 11 and about 5. Between 11 and about 5 or 5 point something. This is the sharp drop happening here. And this means that if we take halfway this sharp drop, we will find that the pH at the equivalence point will be higher than 7. It's between 8 and 9 because the salt formed is basic. So the pH at the equivalence point will also be basic. It will not be at 7 as the previous curve. It will be higher than 7, between 8 and 9. All these points you have to put in mind on drawing your pH titration curves. Since the salt formed here is a basic salt, this means that the equivalence point will happen at a pH which is basic, between 8 and 9, but the same volume as that of sodium hydroxide that we started with. Understand, or shall I repeat?
No, miss, I understand.
Okay. For the titration of a weak acid with, a strong acid with a weak base, let's do this next time, or you are ready to take it now?
How much time do we have left?
Excuse me?
How much time do we have left?
5 minutes?
Is it enough in 5 minutes?
Yes, we can do it.
Okay, miss, continue.
Okay. Now, here in case of the titration of a strong acid with a weak base, we started with a weak base like, for example, ammonia. We take 25 centimeter cube of ammonia, aqueous ammonia solution, having a concentration also of 0.01 mole per decimeter cube. And we are going to titrate it with a strong acid like HCl, also with the same concentration. And since when we react ammonia with HCl, we get ammonium chloride and water. And the reaction here is also in the mole ratio 1:1. This means that also we need 25 centimeter cube of HCl to completely neutralize the 25 centimeter cube of ammonia that were placed in the beaker. So this is the volume of the acid added. It's 25 centimeter cube to reach the equivalence point, the point at which a certain amount of base is completely reacted with the acid. Now, as you see here, the pH curve starts from 11, not from 14 as we used to do before. Here it started from 14 because we were starting with a strong base, which is sodium hydroxide. But here we are starting with a weak base, which is ammonia. That's why we have to start the pH curve from 11, not from 14. Okay. We will see also another observation, that the curve here, when it starts from 14, there is maybe a very, very small gradual change in the pH of the base. But here we will see that there is a big change in the pH from 11.
Because it's a weak base.
Because what is formed here, the salt here, is acidic. Do you have a question?
Yeah.
Yes.
No, it's not.
Okay, so here our salt is acidic, not basic. So when we added HCl to the ammonia, there is a little bit bigger change in pH from 11 to about 9.5 or to 9. A big change from 11 to nearly 9. Why? Because the salt formed is acidic, so it will have an effect on the value of pH. We started with 11, it will reach about 9 by adding more and more of the acid, because the salt formed is acidic. And since the salt formed is acidic, this means that the pH of the equivalence point will also be acidic. It will be lower than 7, in between 5 and 6. So the curve starts from 11, drops a little while, and then the sharp drop will be between about pH 8 and 3. The midpoint will be about 5.5 in between them. This is the pH of the equivalence at the equivalence point because our salt is acidic. So this is the pH at the equivalence point, and the volume of the acid is 25. Okay. If we
Yes, ma'am.
titrate a weak acid against a weak base, both of them are weak. So we start our curve at 11. There will be a very big sharp drop by adding the weak acid, for example, ethanoic acid, and there will only be what we call an inflection point here. We will not have a sharp drop, but we will only have an inflection point here, changing from the basic to the acidic, from the weak basic to the weak acidic state. We don't have a sharp drop as usually we got a sharp drop, but here we just get an inflection changing from the weak base to the weak acid. But also the volume at the equivalence point added from the acid, the weak acid, will be the same as the volume of the weak base that we started by placing it in the conical flask. Understand?
Yes, Miss, understood.
Okay. Then we have to stop here. And next time, inshallah, we are going to see how we will choose